Right, okay. I think that's most people back. There might be a few stragglers. So we're going to start this afternoon with a keynote from Steve from British Steel, which is on tribology of the wheel rail contact.
Okay. Thank you, Jacob. Can everyone hear me okay? Or do I need to speak louder? 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 Right, okay. So my name is Stephen Lewis. I am Rail Technologies Manager at British Steel at the moment. How I got there, I don't quite know. Who gave me the license to be a manager of people? Well, you could, through my story, you'll see how unlikely that's been, but I managed to get there anyway. So, without further ado, I've called this tribology of the wheel rail contact. I think there might have been a mix-up in the communication or something like that, because it's kind of tribology of the wheel rail contact. But anyway, let's go on. So, a bit of an agenda here. So, I'll introduce tribology, I'll introduce the wheel rail contact, I'll talk about some of the damage mechanisms. I don't have enough time to go through them all because there is a lot of damage mechanisms. I'll go through a case study, one. I'd like to do more as well, but unfortunately I just don't have enough time. And just one day for you guys only, we've got some bonus content as well. This is not going to be on Spark, so this is a special treat just for you guys. I thought I might do something that's slightly different. So what is tribology? Tribology is everywhere. It's in everything that we do. It's the science and study of interacting surfaces in motion, in relative motion. It incorporates friction, wear, and lubrication. And you can see a few examples. Just a basic screw in the wall. That is functioning because of tribology. That friction is holding it torsionally into the wall. Bearings, the whole tribo systems are by themselves, but we put them into machines in order to reduce friction. Gearboxes, very analogous to the wheel rail contact itself, and probably the most complicated tribo machine that we make as human beings is the internal combustion engine. A very, very complicated tribo system. There's many tribological interactions going on all the time in one of those things. So that is a whistle-stop tour of tribology. The wheel rail contact is almost as complicated. So we've got a picture of wheel on a rail here, and there are a number of forces that go on in between the wheel and the rail, the interaction. We've got a vertical force, the weight of the vehicle itself, essentially pushing down on the wheel. This can vary as well with different dynamic forces from the suspension of the vehicle. You've got longitudinal force, which is essentially the force that makes the train go or stop. If we didn't have that force, the whole thing wouldn't work. And trains, even though they're going down a straight line, don't always move in a straight line. They're gently rocking back and forth on the rail. That introduces a lateral force, which gives you another force to put into the system. And the whole thing, you can sum up by something that we've coined the term T gamma, which is essentially just a measurement of the energy that's going into the contact. And just like any system, you put energy in, you get energy out. And that energy tends to manifest itself as damage. Just a couple of damage mechanisms there: wear, plastic deformation, rolling contact fatigue, thermal damage. I could add studs and squats to that list. I could add noise and vibration. I could add a corrugation, and I'm sure we'll keep on finding more damage mechanisms to add to that list. To keep this time relatively short, I'll just look at wear and rolling contact fatigue, because they're two quite still big problems that we have to deal with these days. But before we go any further, let's just step out a bit. So I've spent most of my time since I did my PhD looking at the wheel well contact. It's a very small system, but a lot of things going on. And in academia, when I was in academia, I tended to get very focused on just what's going on in that contact. But what's happening in that contact is a result of a much bigger system that's operating outside. You've got suspension, you've got the wheels, you've got the bogey frame itself. There's all sorts of different dynamic things going on there. You've also got what's going on underneath the rail, which we don't tend to really think about a lot when we think about the wheel well contact. The sleepers, the ballast, the track stiffness, and the stiffness of the whole system is things that we should really take into account. So when we look at this system dynamically, so here on one side you've got a plane line running, and you can see the contact between the wheel and the rail is fairly central. It's on the centre of the rail crown and the centre of the wheel tread. It's a relatively big contact. I mean, it's still on the size of a 5-pence piece, but that's relatively big in wheel well contact terms. But the problems start when you start negotiating a curve. So on the outer rail of a tight curve, and you experience this if you drive a car, when you turn around a corner, the weight shifts to the outside of the vehicle. And the same happens with a train. So a lot of that weight of the train shifts to the outer rail. And you can see that the wheel moves its position on the rail. And the problem here is not only have you increased the force on the wheel, you actually reduce the area. The contact breaks up from one contact patch into many smaller contact patches. The other problem that you've got as well is because the contact becomes more conformal, you end up with much more sliding going on because you've got much bigger change in radius diameters across the wheel profile. So you end up with a lot of your damage in that region. You can get a lot of wear, but you can also get rolling contact fatigue generated in that scenario. So rail wear is just like wear in any system. It's a progressive loss of material from the surface of the component you're looking at. And this is what it tends to manifest itself as. In a worst case scenario, you can actually see the imprint of a wheel profile there on the rail. That's a rail that we don't really want to let our rails get to that state. That's a heavily worn rail. We've got different instruments that we can take out into the field to measure 2D profiles of the rail, so we can actually quantify what that wear is. Network rail, most operators allow 14 millimeters of head wear before they recommend replacing the rail. Usually you replace the rail way before you get to that point. So 14 millimeters is where you see that W1. If you measure 14 millimeters down from there, that's essentially theoretically how much material you could lose from the surface. It's going to take a long amount of time. Depends on your operating conditions. It's going to take a long amount of time to get there. But obviously you've got side forces on that rail as well. So it's not just as simple as the wear from the top of the rail. You've got side going on as well. One way to combat wear is to use lubrication, which is what we do in the rail industry. Another way is to boost the hardness of the rail. There's two ways you can do that, the hardness of the wheel and the rail. You can either microalloy the steel, so you can add different elements in there to boost the hardness, or you can heat treat the rail to boost its hardness. So, I forgot to mention, so I'm one of Roger's PhD students. I'm actually PhD student number 2. Roger's second PhD student. That shows how old I am. So this is some of Roger's work. So at low T gammas, so remember T gamma is a reflection of the amount of energy that's going into the contact. So at low T gammas, you get a nice kind of linear relationship between wear and the energy that's going into the contact. But as that goes, as you increase that energy, that relationship starts to break down, and it kind of tapers off for a region. And then as you increase that even further, you get into what we call a catastrophic zone where you get a many orders of magnitude jump in the level of wear. So that is rail wear. Let's have, oh, we've still got a bit more here. So I was talking about hardness. It's one way that we can boost resistance to wear. So you can see here on your x-axis you've got hardness in Brunel, and you've got wear rate, increasing wear rate as you go up the y-axis. So you can see there's a nice relationship up into a point, up to about 370 Brunel, where you get a nice drop in hardness. But after 370, you reach a law of diminishing returns. And as I said, there's two ways that you can boost the hardness of a rail. You can either microalloy or you can heat treat. And sometimes you can do both as well. Most manufacturers tend to do both. So rolling contact fatigue is a different phenomenon. So this tends to happen in the what we call the flange gauge corner contact that happens in the curve. Sorry, David, I'm probably going to butcher this. David knows much more about things like this than me, but it's kind of a whistle-stop tour of rolling contact fatigue. So, as you can see in that central diagram there, that represents a 2D representation of a wheel rail contact. So you've got the contact pressure on the top of the rail, and that creates a subsurface shear stress distribution within the rail. Now, long story short, if your friction is high enough, your peak in subsurface shear stress comes to the top, and that ends up deforming the grains, the perlite grains on the top of the rail, because you're operating beyond the yield stress of the material. Now, you can see in this diagram, this picture down here, this is a microscope picture looking at the subsurface of the rail. You can actually see that grain deformation that's represented by the cracks, and those cracks have been following the grain deformation. Essentially what happens, and apologies in advance, David, your grains get deformed so much that they start to split. You exhaust the ductility of the material, and at some point that will become a crack that's driven by the contact stresses in the head. All good?
Yeah.
Excellent, very good. Right, I don't know what I'm talking about. So, rolling contact fatigue. This is what it presents itself as when we send people out into the field to inspect rails. This is what they see. It's all well and good chopping samples up and looking at them under microscopes in laboratories, but you can't do that in the field. You can only see the surface view. So this is kind of what the rolling contact fatigue cracks look like. And you can do things like you can measure the cracks, you can see how fast they're growing. You have to make a judgment call as to when you're going to replace that rail, or when you're going to employ repair techniques such as grinding, as Lucas was talking about, how you're going to manage it. And this picture here is actually a squat that we're looking at. It's not actually rolling contact, although squatting is a rolling contact fatigue phenomenon, and it illustrates the growth stages of a rolling contact fatigue crack subsurface quite well. So initially you get kind of slow crack growth, and it's not too bad, and you don't really need to worry about a crack when it's in the early stages. The problem is when you reach the end of phase 2. That's the point that you don't want the crack to get to. The rule with cracks, and I can't remember if it's Paris law or something, but the longer the crack gets, the quicker it grows. So you want to keep your cracks nice and short. If they're short, they don't really represent a problem, or they might not anyway. But we'll see in another example they can if there's too many of them. And the final stage is, apologies, I don't think the point is. So the final stage of RCF crack growth is where you get the crack turning down here. Now, I could do a whole presentation on what this is called. Some people refer to it as a Tascheval. I'm not even going to don't get me started on that. But essentially, this crack is going further and further down. It's getting faster and faster, and it's just going to reach the bottom of the rail and cause the rail to break. And most of you here will be too young to remember, but there was something called the Hatfield Rail disaster in 2001. This is essentially what happened. The cracks just got too long, and eventually the rails broke because they're quite a serious derailment. So we don't want to eliminate wear completely, because wear can actually be our friend. Like I was saying, the longer the cracks are, the faster they grow. But if you keep those cracks short, and one way to do that is through wear, you can actually control how quick they grow. And you can actually essentially make cracks dormant by controlling your wear rate, or ensuring that your wear rate is within something. I think someone's talking about this later, the magic wear rate. That might be some other conference I was thinking about. So there's quite a nice interaction there between the two. This shows the interaction between wear and RCF. So along the bottom here, you've got the curvature. So you've got a sharp curve, which is represented by this sharp curve here over this end, and then you've got shallow curve over this end, which is represented by these more shallow lines here. So when you've got a sharp curve, you tend to be dominated by wear. So you haven't got much to worry about with wear. Wear's nice and stable and predictable, and we can kind of measure it, and it's not a major problem. The problem comes when you start to relax the curve radii, because you start then getting RCF dominating as your main failure mechanism in the rail. We don't like RCF because it's not as predictable as wear. It's a bit less. It can cause rails to break at any time. It's not as easy to measure. Like I showed in the picture a few slides ago, you can only measure it from the surface. You can't really see what the crack is doing below the surface. You have got techniques like eddy current and ultrasonics, which can give you some information, but it doesn't give you a detailed picture like you get underneath the microscope. So why don't we just use harder rails? Surely that's the answer. Well, one answer is here, and this is research that was done by the university. And this is a result of twin disc testing, and I keep losing my eyes when I'm doing this. So this is the number of cycles of the test, and this is the wear rate. The higher the number, the more wear you're getting. And there's three different materials represented on that chart. You've got R260, which is basically the standard rail used throughout most of Europe. The number represents the hardness of the rail in Brunel. So the bigger the number, the harder the rail is. There's HP335, which if I can find my license again, that's British Steel's premium product, premium rail steel. 335 hardness. It's a microalloyed, naturally cooled, so it's not heat treated. It's not a heat treated product. And there are pros and cons to heat treated products or not, which I haven't got time to go into. And then the nearest competitor to HP335 is R350HT, and the HT stands for heat treatment. So obviously the 350 is harder than the 335, but actually after about 20,000 cycles, you get lower wear from the softer of the two premium rails. So hardness is not always the answer, and it's something that we don't quite understand. I think, dare I say, we've been a bit lazy in tribology up to this point, just assuming that hardness is the answer to everything. Hardness is just a number, and if you think about the Archer's wear equation, you stick a, dare I say, fudge factor on the front of it. Well, what's in that fudge factor? Where does that come from? There must be something else in there that we don't quite understand. The microstructure, the surface tension, the surface energy, it could be anything. So if there's an area that I think needs investigating, it's this. It's what's the next level after hardness. So I'll look at the case study now, and how am I doing for time? So this was our HP335 rail that was installed at London Underground in 2017, I think. It's HP335 we launched in 2011, and it's been installed successfully in Network Rail since then. We've had good feedback from the customer that it's performing very well. So London Underground got wind of the product, and this is what one of their rails at this particular site looked like. And apology for the quality of the picture, but this is the rail head. And on the central crown of the rail here, there's a very dense band of rolling contact fatigue cracks. And the reason these cracks are a problem is not necessarily because they're too deep, it's because they're too dense. And the problem with that is that they block ultrasonic signals from penetrating the rail. So essentially you can't see if there's any defects in the rail below that layer of rolling contact fatigue cracks. So what they have to do at this particular location in London Underground is they have to throw away rails that have got lots of life left because they can't safely test them. They just don't know what's going on below. So they were thinking, right, well, let's just use a harder rail to solve that problem. The rail, if we increase the rail hardness, the cracks are going to grow, they're going to develop slower, which is what we've seen at Network Rail. Let's try it. But then this is what happened. So this is a fatigue crack, what some again might call a Tasha valve. But let's not go there. In the rail. And this is a very, very deep crack. Now, this rail hadn't broken. It was still in one piece. So one positive for HP here is that this crack was growing slowly enough that it gave London Underground engineers enough time to go out and put emergency speed restrictions in place and rectify the problem. So you can see here there was 13 cracks within a 2.5 metre section of this particular section of track. So when we looked at the cracks underneath the microscope, this is kind of what we saw. You can see the cracks are going straight down, which is atypical of normal rolling contact fatigue cracks. They tend to grow at a shallow angle to start with relative to the surface, and then they turn down. Well, these cracks were going straight down into the rail, but they were also quite close together. And you can see that you've got some H-shape joining of the cracks. These are the bits that block your ultrasonic signals and mean that you can't see what's going on below there. Now, what's unique about this location is it's between Cannon Street and Mansion House. And there's actually videos on YouTube, I've not seen them, but people have set themselves challenges that it's actually quicker at peak time to get off at Cannon Street, run to Mansion House and get back on the same train. I've not seen the videos, but what you've got is, someone said drive it like you stole it earlier in one of the presentations. That tends to be what London Underground drivers do. And the other problem they've got at London Underground is automatic train operation mimics that behaviour as well. They've either got an on-off switch, it's either full throttle or full brake. And you end up with this very unique situation where when the train sets off from here, the front end of the train will be accelerating around this curve. But the back end of the train is braking around the same curve as it comes into the next station. So you get some very complicated forces going on in the wheel-load contact in this location. So, as you'll find out, there's a theme through my life, and I should have renamed this presentation and called it "How to Get Chucked In at the Deep End," something like that, because it tends to just happen. This was the first project I got when I went to British Steel. It's like, Steve, we've got our flagship product. It's not performing very well. Can you sort it out? Yeah, okay, I'll give it a go. So I thought, well, let's compare to R260. How is R260 behaving in the same location? And you can see the cracks, they're not too dissimilar. They're a bit more shallow, but then they tend to join up and you've got chunks of material falling out of the surface. And you can see here how the ultrasonic signals are getting blocked by these cracks, which is why you've got to throw the rail away before its useful life is up. And then I want to compare that with a completely different situation. So this is a power station. The axle loads of this power station are 25 tons. The axle loads on London Underground are no more than 8.5 tons. So you can see the cracks are much more widely spread between each other. They've still got the same morphology, they're still fairly vertical, but they're much wider between each other. You've got much more wear happening at this site because you've got fully laden freight trains going around a very tight curve, putting lots of wear into your material. So a summary of this is going back to our old friend of rolling contact fatigue versus wear. This is what I think was happening at this location in London. When they had R260, they were operating just at this side of the central line. So this is the failure by rolling contact fatigue. Your damage mechanism is dominated by rolling contact fatigue. We don't want to be in that region because it's unpredictable. We want to be on, ideally, we just want to be just this side of the line where we're controlled by wear, which is much more quantifiable, measurable, predictable. So with R260, they were operating here, just on the wrong side of the line. Now, in hindsight, we didn't know, by increasing harder rail, whether that would put us to one side of the line or not. But essentially what's happened is the HP335 has just pushed them further into the fatigue regime. Really, I think what the solution here is a downwards, what would be considered a backward step, an R220, a rail grade that's not been used in Europe for quite a long time. It's still made here and now. I think they use it in France. In France, they actually use this philosophy of using a softer rail to combat rolling contact fatigue. So that is essentially a whistle-stop tour of the wheel rail contact tribology. I'm just trying to put my teeth in. I'd love to go